Okay, now one of our special types of discrete random variables is called a binomial random variable, and more specifically, we're going to be looking at the binomial distribution. Now, on our handy dandy formula sheet, we see here from descriptive statistics, we've learned Unit 1 and Unit 2, and we started off in Unit 4 with our general addition rule and our conditional probability rule, and now this is the next half of Unit 4, which is the random variable stuff. Oops, sorry, hiccups, I'm full from lunch. But here's our discrete random variable, right, mu x and sigma x, and we've been practicing these formulas. But now here we are with a special case, which is the binomial distribution with parameters n and p. Now it has a scary looking formula, but I promise you once I teach you how to do this, it's not that bad. And notice x can be 0 through n, and then we have some new parameters as well. So let's actually learn what a binomial random variable is. Well, when the same chance process is repeated several times, we are often interested in whether a particular outcome does or does not happen on each repetition. Some random variables count the number of times the outcome of interest occurs in a fixed number of repetitions. This is what we call a binomial random variable. Now, there are 4 conditions for the binomial random variable. And the first one is that it is binary. That means that each trial can be defined as a success or a failure, meaning it does happen or it does not happen, right? Very similar to our complement rule. And now success doesn't always mean a good thing, because this could be the outcome that you're bankrupt. So success, failure, success just means it does happen, failure means it does not happen. It's complement. Next up, they have to be independent, which means knowing the results of one might not tell us anything about the results of the next, such as flipping a coin, rolling a dice, randomly selecting from different towns, etc. Next up, n and p are the parameters that we saw. N is fixed, meaning that the number of trials is discrete. So maybe I'm interviewing 10 people. Maybe I'm only selecting 20 pieces of candy. Maybe I'm looking at a random sample of 100 different tires, etc. But n is fixed and it's discrete, meaning it's countable. So I can have none, 1, 2, 3, up to this nth trial. And then p is the probability of success. But again, it's independent, so that means it doesn't change from observation to observation. So we call this the bins. So binary, independent, n fixed, and s for success probability. Now, if all 4 of these conditions are met, we are going to say that x is distributed with a binomial distribution with parameters n, p. So notice this is very similar to x is distributed normally with mu sigma. So now we are showing different distributions. So let's look here. Again, I am trying to see if it meets the bins criteria. Now, they're not going to ask you this on the AP exam, but come on, we got to know all the theory before we learn all the fun stuff. So, drawing a red card without replacement from a standard deck of cards. Well, it is binary because my options are either red or black. Now, we're not going to be independent because of this key phrase right here, the without replacement. That is no bueno. That means the probability is going to be changing each trial, right? This is now a successive dependent event. And fixed, well, let's think about this. There are only 52 cards in a standard deck, and of those 52, 26 are red. And then the probability of success, well, these are dependent events, so that is not going to meet our criteria. So unfortunately, I tried to draw a bracket, that kind of looked like a nose. Unfortunately, that means no binomial, no bins. So let's take a look at the second scenario. Shuffle a deck of cards, turn over the top card, put the card back in the deck, and shuffle again. Repeat this process 10 times. And sorry, but drawing a red card, then doing this. My apologies. Typo. So let's see now if we meet the bins criteria here. So binary, check because we are red or we're black. Independent, well, check because it looks like we're putting the card back. So we are doing this with replacement. And fixed, yep, because look, we are doing this 10 times. And then the probability of success is also going to be there because theoretically, the probability of selecting a red would be 26 of the cards out of 52. So just being able to distinguish binomial will allow us to proceed with what procedure we're going to use. And this is important because now think about this. In Unit 4, we've learned all different types of probability, starting from a general probability model to the addition rule, to the complement rule, to conditional probability, to probability trees, to successive independent, successive dependent, mutually exclusive. Then we did random variables, combining random variables, transforming random variables, and now a discrete random variable. Like, wow, so much math, a lot of love. We're going to get it together, no worries all. So let's take a look, though, at what this might look like in context of a question. In a binomial setting, we can define a random variable x as the number of successes in n independent trials. We're interested in finding the probability distribution of x. So suppose each child of a particular pair of parents has probability 0.25 of having type O blood. Genetics says that children receive genes from each of their parents independently. And if these parents have 5 children, the count of x children with type O blood is a binomial random variable with n equals 5 trials and probability p equals 0.25 of a success on each trial. In this setting, a child with type O blood is our success and a child with another blood type is failure, right? This idea of a complement. Find the probability that x equals 2, which x is, find the probability we have 2 children with O blood. Well, let's think about this. They're independent, right? Which means I can just keep multiplying them. So if I want 2 kids, and I'm going to write this in red. Do not write this down. I'm just showing you my thinking here. So let's say I have 2 kids. That's going to give me 0.25 times 0.25. And then I'm going to have 3 kids that do not have the O blood. So I should, in theory, get a probability of about 0.0264. Now, I'm good, right? Except, no, because why else would I ask you this? Well, let's think about our sample space. Notice that in my probability statement, I do want the probability x is 2. But there's 5 kids in the sample space. So that means child 1, child 2, child 3, child 4, and child 5. So in my sample space, I'm going to make this like fancy looking S. In my sample space, there are some different combinations that we could happen. In here, I'm assuming that my successes happen on the first 2 kids. That means child 1 and child 2 have O blood, but then child 3, 4, and 5 do not have O blood. Well, what if that's not the case? What if, for example, child 1 doesn't have O blood, child 2 does, child 3 does not, child 4 does, child 5 does not? That could happen. We could also have maybe that the first one doesn't have it, but child 2 and child 3 have it, and then 4 and 5 don't have it. Or maybe, I don't know, maybe the first and second don't have it, and then child 3 and 4 have it, but not child 5. Or let's see, how about first and middle? How about first and fourth? How about first and fifth? How about second and fifth? Or let's think maybe if the first 2 could have it, what if the last 2 have it? Or what if the third and the 5th one have it? So this is my sample space, right? These are all possible outcomes where this could happen, in which we have different variations. So this is true, regardless of which combination I use, the probability will be 0.0264. Now, this assumes that these are not the only outcomes, right? Because maybe all 5 of them have it, or maybe all 5 of them do not have it. I'm just looking at the instance in which only 2 of them have it. So this is going to be the sample space of exactly 2. Exactly 2 have it. So that means, let's see, there are 10 outcomes. So I'm going to take now 10 times the probability of this happening, which means it's going to give me a probability of about 26% chance that exactly 2 of my 5 children are going to have O blood type. So how are we going to have to write this out every single time? Oh, definitely not. We're actually going to use a few shortcuts, and we are, it kills Mr. Pinto's heart, but we are going to be using the calculator for these types of calculations just because it's a little bit more effective. Now, you do need to be prepared to set up the formula from the formula sheet, but your computations can yield full credit from calculator output. So this fancy way that I determine all these combinations, this is what we call the binomial coefficient. Now, in the previous example, any arrangement of 2 successes and 3 failures had the same probability, because that was true no matter what the arrangement was. We multiply the 0.25 twice, and we multiply the 0.75 3 times. Well, we can generalize this in any setting where there's k successes and n trials, And we're not going to use k, we're actually going to use x successes because that's right. I'm looking for the probability that x is this. So from our formula sheet, we can see that it's right here, n choose x. That is the binomial coefficient. And n choose x is given to us as n factorial over x factorial times n minus x factorial. You do not need to get this detailed for the AP exam. You just got to know how to push a few buttons. But notice that it starts at 0, right? I can have either none of my children have O blood type, or one of them does, or two of them does, up to 5 children having it. So let's now use this binomial coefficient to solve some problems. So this is our binomial model. Again, I just pulled this from my AP Stats formula sheet. And I want to find the probability that exactly 3. So when we've been working with probabilities, we've only really worked with 3 types of inequalities, either a below, an above, or a between. But now with discrete random variables, I can actually find the probability that x is a specific number. Because again, I have child 1, child 2, child 3, child 4, and child 5. And then within each of these, I have a success or failure for all 5 children. Okay, so n is 5. We got to define our parameters. So x is going to be binomial, where n is 5 and p is 0.25. Okay, so n choose x. That means that I have 5 choose 3 times 0.25 of 3 successes times 0.75 of 2 successes. I'm going to show you how to do this in the calculator. Just not on this video because I don't have all my fancy stuff, but if you just had a regular calculator, there's a C button, a CN button on your calculator. This will produce the same answer. Now, I know you're like, wait, what if I don't have a fancy calculator? You don't need a fancy calculator. I'm going to teach you all the math behind it in class, though, since this is our virtual stuff, not as detailed. So for those of you who have stumbled onto this YouTube channel, my bad. But here we are. So the probability that we have exactly 3 children with type O blood is going to be 5 choose 3 times 0.25 cubed, because 3 of the children have it, times 0.75 squared, because 2 of the children will not have it. And now, suppose the parents are going to be surprised if more than 3 of their children have type O. So let's find the probability that P is greater than, right? P of X is greater than 3. So if P of X is greater than 3, remember that I have 5 kids, and of those 5 kids, the ones that are greater than 3 are going to be these 2, right? That there's more than 3 kids that have it. That means that either, sorry, not just those 2 positions, but that means that either 4 of my children have it, or even all 5 of my children have it. So I don't care which 3 have it, I just care that 3 had it. So in this next scenario, we're looking at the probability that either 4 have them or 5 have them. And I'm just going to show the formula here. But again, I will teach you how to use the calculator in a bit. So 0.25 to the 4th times 0.75 plus 5 choose 5. Notice not 5 divided by 5. 0.25 to the 5th, because we have 5 successes and then no failures. Well, I'm going to take 0.0146 plus 0.0009, which are given to me from the calculator. And when I add these 2 numbers together, I get a very tiny probability of about 0.0155. This is very unlikely to occur by chance, so I would be very surprised if I end up with more than 3 kids who have type O blood. So that's the thinking there. I'm pretty sure this example went a little too quickly, so I'm going to actually film a video later that's going to have all the calculator steps that you're going to need. Now, it's going to be done using an Nspire, so for those of you with the TI, you're going to need to find a different support video. So sorry. But that's a little bit more on binomial probabilities. In the next video, we're going to talk about the parameters of a binomial distribution. So stay tuned.